This video is about the tangential and normal components of acceleration, and also about the unit tangent vector and the unit normal vector. In the last video, we proved this fact. If a vector dotted with itself is equal to a constant, then it turns out that that vector and its derivative is equal to 0. Let's think a little bit more about the implications of this statement. This first part says that a vector dotted with itself is a constant. Now, geometrically what that means is that if I take R and I dot it with itself, so that's going to be the x component of R times the x component of R, plus the y component of R times the y component of R, plus the z component of R times the z component of R if I'm in 3D. If I'm in ND, this pattern continues. I just have n terms instead of 3. Now that is almost exactly the same thing as the length of the vector R. The length of the vector R is this. So if I take that length and I square it, it turns out that I'm getting r dot r back. So this is the length of r of t squared. Okay, so with that in mind, when I see r dot r equals a constant, what this is telling me is that the length of r, or more specifically, the length of r squared is equal to a constant. And if the length of r squared is equal to a constant, or the magnitude of r squared is equal to a constant, well then the magnitude is equal to a constant. So we're keeping all of that in mind. And now let's restate this. We're saying if the magnitude of r is constant, then it has to be the case that r and its derivative, when you take their dot product, you get 0. Now this can be interpreted as these two vectors being orthogonal to each other. So I've got r of t right here. This is saying if the length of r stays the same, when r changes, its derivative acts in a perpendicular direction. Those two vectors are orthogonal to each other every time. So if r is like this and it's changing in this direction, maybe it's turning this way at a different time t, r prime is this way. Now if r looked like this and it was going in that direction at a different time t, r prime would be that way. But if the magnitude of r is constant, then that vector r and its derivative are going to be meeting at a perpendicular direction. I also like to think about the contrapositive of this. If these two guys, if r and its derivative weren't acting in perpendicular directions like this, if some part of the derivative was acting parallel to r, well that's going to force r to be longer or shorter. If I had some part of the derivative that was acting this way, well then the new r would be a little bit longer. Or if I had some part of the derivative that was acting in the opposite direction from r, the new r would be shorter. So this is saying that if r stays exactly the same length, then those have to meet at 90-degree angles. Or alternatively, if they don't meet at a 90-degree angle, so that the dot product's not 0, then the length of that vector has to change. So all this is important, and we want to keep it in mind as we think about what are called the unit tangent and unit normal vectors of our function. So let's say you've got r of t, a vector valued function or a vector function, and maybe it lives in n-dimensional space. In our class we tend to stay in 2-dimensional space or 3-dimensional space. I'm going to draw it in 3-dimensional space. So remember how this works. R is taking some point in the domain, which is a subset of the real numbers, and it's mapping it to a vector in three-dimensional space, but we're just looking at the terminal point of that vector. So we're actually mapping to a point in three-dimensional space. So instead of writing this, I could write, what we're taking is a number t, and we're mapping it to a point, x of t, y of t if we're in 2D, x of t, y of t, z of t if we're in 3D, x sub 1, x sub 2, x sub 3, all the way through x sub n if we're in ND. But we're just taking a single real number and we're mapping it to this point in n-dimensional space, and specifically we're going to look at three-dimensional space. So as t increases, you're mapping out this ordered triple, all these different points in space, and you might have a path that looks something like this. So maybe as t increases, you're going on a path like this, and remember r of t is a vector. We sometimes call it the position vector. I like to think of it like that sign in the mall. It says you are here. So r of t points to your location. And we normally don't draw this vector, we just draw the location at a particular time or at a particular location. Now that does not have to represent time, but it's convenient to think of assigning a time to a particular location. If this is the position of some object at time t, at a certain time it's over here, and then a little bit later that object is over here, and as time increases we're just tracing out this curve. And r of t is a vector that starts at the origin and points to that location and tells you where you're at. So it is the you are here vector. Okay, now we said in the last couple of videos when we talked about differentiation that r prime of t, let's say r prime of t naught, is tangent to the curve. So it's a vector tangent to the curve. And I'm going to call my curve C. Generated by our vector valued function, or our vector function r of t. And it's tangent to the curve at the point of tangency, at t equals t naught. So it's going to be tangent to the curve at p of t naught, which is going to be the terminal point of r of t naught. So it'll be x of t naught, y of t naught, z of t naught. So maybe instead of just thinking of this as r of t mapping to a point x of t, y of t, z of t, maybe we're thinking of a particular time. Then this is x of t naught, y of t naught, z of t naught. At that time, r prime of t naught is going to be tangent to the curve. It looks like I pretty much made it vertical. So there's r prime of t naught. Or it's on its side like that, so you can read it like that. It's tangent to the curve, and it points in the direction of increasing t. So if this is r of t naught, and as t increases, we're traveling along this curve, r prime of t naught looks like this, and it tells you which direction that you're going in. It indicates the direction that you're traveling along this curve. So we also said if r of t is position at time t, its derivative is the velocity at time t. And of course, if I plug in t naught, I can find the velocity at a particular t. Now, the unit tangent is actually very easy to define. It's a tangent vector to the curve at time t equals t naught, or at time t. It's a tangent vector to the curve, but it's 1 unit long. So we define it this way. I'm going to call it t hat of t, and it's going to be given by r prime of t, that's the tangent vector, or the velocity vector. And then we're going to take that velocity vector, or the tangent vector, and we're going to divide by its magnitude to make it 1 unit long. I tend to think of t hat this way, but remember r prime is velocity, so if you prefer, you could call that the velocity divided by the magnitude of the velocity. Or, in words, we could call this velocity, which tells us the direction that we're going, divided by the speed. So now I've got a vector that just points in the direction that we're traveling in. Provided that r is position and t is time, this unit tangent vector points in the direction of motion. Okay, so that's the unit tangent. Now we're going to put a couple of things together, a couple of ideas together. The unit tangent vector, no matter what t is, it's 1 unit long. By design, I take a vector, I divide it by its length, and now it's 1 unit long all the time. Well, according to this fact that we looked at earlier on the last video, if I have a vector that's 1 unit long all the time, so its magnitude is constant, then that vector dotted with its derivative is equal to 0. Or, alternatively, you can think of this geometrically. Well, we had it up here. This is not geometric. This is more geometric. This says if I take the dot product of a vector with itself and I get a constant, then the dot product of that vector and its derivative is 0. And what this means is the length of the vector is constant. And what this means is when I look at that vector and I look at its rate of change, the rate of change acts in at a 90-degree angle to the original vector. So applying that to our unit tangent vector, since the length of my unit tangent is always equal to 1, that unit tangent and its derivative always meet at 90-degree angles. So let's say we're on some curve like this. Unit tangent is right here. Then sometime later, the unit tangent is going to be right there. It's going to be the same length, but at a slightly different location. Now, the t hat prime is meeting that at a 90-degree angle. And I know these two vectors, they don't look like the difference between them is like given by this derivative t hat prime of t, but it is. These two vectors have exactly the same length, but when this vector t hat changes by a little bit, its initial point also changes. So we're seeing a lot more going on there than really is going on. If I were to fix my t hat with its initial point at the origin, as it changes, as we go along this curve, well, t hat's going to start, it's going to go, well, it's pointing like this. It looks like the slope is getting closer to 0, and then the slope is becoming negative, at least in 2D. That's exactly what we're seeing. But as we're going up this curve, notice that the terminal point of that t hat is going down a little bit. So t hat prime is pointing this way. So t hat prime is perpendicular to t hat, and it points in the direction that we're turning. So we say that this is orthogonal to t hat. And it points in the direction that we're turning. And my significant other just came home. That's okay. That's life, guys. All right. Okay, so t hat and t hat prime meet at 90-degree angles. We define another vector based on that. We call it the unit normal vector. So we know that this is perpendicular to this or orthogonal to this. In order to make it 1 unit long, we just divide by its length, and we call that the unit normal. So right now I've got t hat is the derivative divided by its length or magnitude, or if you prefer to think of it physically, that's the velocity divided by the magnitude of the velocity or the speed. So this is the unit tangent vector. It points in the direction of motion. It's the way we're going. And then using that fact, what seemed to be completely unrelated, just this little fact about dot products, little dot product proof that we did in the last video, we were able to show that there's another vector, n hat. And that's perpendicular to t hat. And if I want to make it 1 unit long, I divide by its length, or magnitude, same thing. And this points in the direction that we're turning. And I think that makes sense, because if t hat is pointing this way and n hat goes this way, remember that's t hat prime divided by its length. Well, if my t hat is changing by this in this direction, well, the next t hat is going to go that way. Instead of going this way, it's going to go a little bit that way. So I'm turning that way. I've got a curve that's going that way. Now, if the vector is pointing in the opposite direction, well, that means, well, my t hat has to change in this direction, so I'd be turning that way. So whichever way n points, that's the direction that we're turning. So it might look like that as t increases, or the other option, from some angle, from some point of view, it might look like this. So my t hat changes by a little bit. Call that t hat prime. We normalize it. Normalizing, I know it seems like it's related to the normal vector. It's not. Normalizing a vector just means making it 1 unit long by dividing by its length. So this is the rate of change of this vector, and we made it 1 unit long. Okay, so now let's talk about acceleration. Now this is a fact that you'll see in all of the calculus books. It says that the acceleration vector lies in the plane defined by 2 vectors, defined by t hat and n hat. Okay. And one way that we can come up with this, one way that we can prove this to ourselves, is to just look at the acceleration vector and say, okay, well, that's the derivative of the velocity vector. And the velocity vector can be defined in terms of t hat. Just remember, t hat is just the velocity divided by its length. So if I solve for velocity, it's just going to be the length of the velocity vector times t hat. Or if you prefer to think physically, that's the speed. The magnitude of the velocity is the speed. And we're multiplying it by t hat. That's the direction that we're going. So acceleration is defined to be the derivative of velocity, which I can now think of as the speed times that unit tangent, which points in the direction of motion. Now, I did not prove this in the last video, but you could easily prove it to yourself. If you've got a scalar function here and a vector function here, there's a product rule that applies to that. You might say that, like, that's not intuitive. Well, you should check it out. If you don't believe me, you should go through the derivation. But it works just like the regular product rule. If this is my first function and that's my second function, according to this product rule for scalar functions times vector functions, we get the derivative of the first times the second plus the derivative of the second times the first. And watch this. That's just a constant times t hat. So that means part of my acceleration is acting in the direction of t hat, and that constant that's going to be multiplying that direction vector is this one, and we're going to talk about what that means in a little bit. And then over here I've got the magnitude of the velocity, which is the speed, and the derivative of t hat, well, I just call that t hat prime. Well, we know that that's related to the unit normal based on how we just defined it. The unit normal is this vector that points in the direction that we're turning, divided by its magnitude. So I can take this and make it a unit normal by dividing by the magnitude, as long as I compensate for that by multiplying by the magnitude. So now we've got this. That's my unit normal. And this is the derivative of t hat with respect to t, and we're finding its magnitude. And that's just a number. Now, in a different video, we talked about the arc length parameter. We talked about S. Now, by the chain rule, I can rewrite this derivative of t hat prime slightly differently. I can say that that's the same thing as, this is the derivative of t with respect to little t. Instead of doing that, I could take the derivative of t hat with respect to the arc length parameter, S. So this is the change in the unit tangent as we go a little distance, a little length along our curve, as long as I multiply by ds dt. And that's an instantaneous change in distance traveled along the curve per unit time. Okay, let's think about what that is. What is the magnitude of this? The magnitude of distance traveled along the curve per unit time. I hope you said speed. If you did, you're right. That's speed. So I've got speed times speed, and this is the derivative of the unit tangent with respect to arc length. I'm going to take its magnitude, and we're multiplying that all by n hat. So let me write out on the side what we just did. We were just trying to get an n hat right there. Right here we used the chain rule. So this is the derivative of t hat with respect to arc length times the change in arc length with respect to time, or if you prefer, change in distance traveled along the curve with respect to time. And then I just told you that ds dt is equal to the speed. And if you don't believe me, Maybe you can look back at your notes over arc length. Remember when we defined the arc length parameter in a different video? We said the arc length is the integral from t naught to t of the magnitude of r prime of some dummy variable. I think our textbook author uses the letter tau. Some textbooks use u. It's just a dummy variable we're integrating with respect to. So I've got the magnitude of r prime of tau times d tau right here. By the second part of the fundamental theorem of calculus, if this is a constant and that tau is just a dummy variable, and this is my true variable so that my arc length is a function of time, or this is my distance traveled along the curve as a function of time, it's how far I've gone after so much time, then the derivative of this variable with respect to that variable, ds dt, is just this integrand, but instead of having a tau there, you're going to replace it with a t. That's the second part of the fundamental, or second part or first part of the fundamental theorem, depending on which textbook you use. Well, that is the velocity, and the magnitude of velocity is speed. So that's what I've used right here. Okay, so let's get back to acceleration. So now we see this. Acceleration is this constant times t hat plus this constant times n hat. And I think that's exactly what we were trying to prove. If acceleration is a constant times t hat plus a different constant times n hat, well then it has to lie in the plane that is created by t hat and n hat. In linear algebra, we say it's the plane that's spanned by those two vectors. So let's say this is our curve. And at this point, our unit tangent is pointing this way. And our unit normal, it's pointing in the direction that we're turning. It's pointing this way. Now, according to this formula, our acceleration can be broken down into two components. It's going to have one component in the direction of motion, plus another component in the direction of this unit normal. So maybe it looks like this. I'm not actually sure what it looks like for this particular curve. I'm just going to draw it. So it's got one component parallel to the direction of motion, and I'm going to call that, this constant in front, a sub t. So this vector is a sub t times t hat. And then what I add to that to get acceleration back is this vector. That is the normal component of acceleration, the normal vector component of acceleration. And it's going to be this constant, which we're going to call a sub n times n hat. So this is telling us that a lies in this plane. T hat is pointing in the direction we're going, and we've already talked about the fact that n hat is pointing in the direction we're turning, because it's really just a normalized version of t hat prime, and t hat prime always has to point in the direction that t hat is changing in. So t hat's changing a little bit this way, and this is the original t hat. Our acceleration has one part that's going in the direction of motion, plus another part that's going in the direction that we're turning. And those two parts are called a sub t times t hat and a sub n times n hat, if we're looking at the vector components, or the scalar components are just these two numbers. That's a sub t and a sub n. So let's talk about what these mean. I think it's easiest to understand what a sub t and a sub n mean by looking at these formulas and also thinking about the very special cases. Let's think about if a sub t were equal to 0 and our acceleration was entirely in the normal direction. And then let's think about if a sub n were equal to 0 and a sub t were entirely in the direction of the unit tangent. And then we'll analyze these formulas and interpret them physically. Okay, so first special case. Let's assume that a sub n is 0 and a sub t is not 0. Now, if a sub n is 0, that means a, our acceleration vector, is just a sub t times t hat. So all of our acceleration is in the same direction as the direction we're moving. Now, if this is our unit tangent, and the acceleration is in the same direction. Remember, the unit tangent is the direction that we're going. If we're also accelerating in that direction, it makes perfect sense that we're changing our speed. We're speeding up. Now, if our unit tangent is heading that way, and our acceleration is going in the opposite direction, it's like coming up to a stoplight. We're continuing to go forward, but we're slowing down. So this is leading to speeding up, this is leading to slowing down, and since there is no normal component, we're not turning at all. We're either speeding up or slowing down in the direction of motion. So it makes perfect sense when I look at this formula and I see that a sub t, that's called the tangential component of acceleration, and I guess we should be more specific, it's the scalar tangential component of acceleration. This leads to changes in speed. And according to our formula, which we just found using a product rule, a sub t turned out to be the derivative with respect to time of the speed. So it makes perfect sense that that would lead to changes in speed. If we're not changing, if our speed isn't changing at all, well, this is going to be 0. And that makes sense because our velocity vector is not going to be changing, not in that direction anyway. Now, if we are speeding up, that's going to be a positive number, and we're going to be going more in this direction. If we're slowing down, it's going to be a negative number, and so my acceleration is going in the opposite direction. So whenever you see an a sub t, think of it as interpreting it in terms of change in speed. Now, the other special case is that a sub t could be 0, and a sub n might be non-zero. Well, if a sub t is 0, well, we just said, well, that's the derivative of speed with respect to time. If that's 0, that means our speed must be constant. So we're moving at a constant speed, and our acceleration is entirely in the normal direction in this case. So we're traveling along some path, and this is our unit tangent, and our unit normal is pointing in the direction that we're turning, and all of our acceleration is pointing in that direction. Well, I think we can see just from this picture it's going to lead to turning, and it turns out that it's going to lead to turning around in a perfect circle, because our speed isn't changing. So we call this a sub n. This is the scalar normal component of acceleration. It acts in the direction that you're turning. And if it's non-zero, it always leads to turning. Now let's look at that formula. A sub n was the magnitude of speed squared times this other magnitude. And we haven't talked about this yet, but this is the magnitude of the derivative of the unit tangent with respect to arc length. Later we're going to call this curvature. And I think that this makes physical, intuitive sense. Let's say you're driving along a curve and you're taking a very sharp turn. You're going to feel a huge centripetal acceleration in your car, right? There's a big part of your acceleration that's pulling you this way, and you're going to feel like you're being pushed out in the opposite direction just to compensate for that acceleration. Well, if you don't want to feel that way, what do? You're going to do one of two things. You're either going to lower your speed, and that will reduce this normal component of acceleration. If you lower your speed, it won't be so bad. Or you can just take a wider turn. And this curvature, it's some indication of how wide that turn is. If the curvature is 0, you're going on a straight path. If the curvature is something other than 0, and it's always greater than or equal to 0 because it's a magnitude. If your curvature is non-zero, then you're turning. And the larger that curvature becomes, the sharper that turn is. And again, it makes sense that if this was non-zero, if the normal component of acceleration is not equal to 0, then there has to be some curvature. Because if there weren't curvature, then this would be 0, and if this is 0, then we're not turning at all. So a sub n is the curvature times the speed squared. So that's how we interpret those two guys. A sub n acts in the direction that we're turning, and notice from the formula that it is always greater than or equal to 0. So our acceleration always acts, or always has a component in the direction of the unit normal, or none at all. It never acts in the opposite direction of the unit normal. And then this guy, a sub t times t hat, leads to changes in speed. Now most of the time you're not dealing with either of these special cases. You might have both of these together. Your acceleration is composed of these two components. One part is leading to changes in speed along the direction of motion, and the other part is causing you to turn. Now in the next video, we're going to talk about the most efficient way to calculate all of this. This is very good for physical interpretation of what a sub t means, and this is also a very good way to calculate what a sub t means, or a sub n means, but it's probably not the most efficient way to find a sub t or a sub n. So I'm going to give you some simple formulas for calculating these, and then we're going to use these formulas to interpret those numbers when we're done.